guys one lecture in the first week. And let's just go back just a little bit to it. I was saying I was going to cover use of material and through examples, but also trying to put it all together. If you remember, we had this example with the X-ray source. I was describing that they made a change where they were going to turn on and off the switch very fast, and that essentially changed the way the source was breaking, and they had to go back. One thing that I think ties into today's lecture is if you do have history of service, lots of times you can save a lot of these steps. And what I mean these steps is you have material selection, then you go and specify. That is the material. Sometimes it's the process, how the pieces are going to be put together. You're going to require some quality control. Once all of that is established, a lot of times you have to make sure before you go and get it built that you're going to be strong enough. Whatever the characteristic is, if it's just corrosion resistance, is the environment going to be too corrosive for the material, for example. And then there is service, and that's where the whole history comes in, because when a component or a system's been used a long time, you gain information, and sometimes you can feed back and say, well, we really didn't pick the right material, or oops, we didn't say exactly how to control the quality, so we just had a quality issue. So from here you can go back to any level, essentially, and hopefully find the solution quickly to make sure that you have the right material and process for the application. So what I want to do today is give you guys some example, but I want to talk more about the material selection part. And one way we're going to do it first is talk about how you select material for aircrafts. And it's not to say that any of you will necessarily need to do that, but one reason that I'm bringing it up as the first topic, it's very well known. It's one of these areas where people have been spending a lot of time looking into different categories of alloy, different ways to put materials together, because it's very expensive, both in terms of material and in terms of processing. So when I say expensive, there's a breakdown of cost, and it's not exactly up to date. I'm sure these things do change a little bit. But if you think about the cost of buying and owning an aircraft through its life cycle, I think this is annualized, so interest is taking into account. But what I want to bring up to you is the cost of material is only 3%. The cost of the design is 6%, and then the cost of manufacturing is more than the two of the others together. They put the engine separate. Another big aspect of the cost here is the fuel. That may have changed recently, but if you go to weight, for example, you spend as much money on fuel through service that you spend on the initial manufacturing. So this is one of those few examples. If you remember on the first introduction class, I said a lot of times we try to minimize cost. But for aircrafts, minimizing cost takes a slightly different dimension, because it means reducing weight. It means also fulfill the overall function. So if nothing else, what I'd like you to take on in terms of the material selection part here is, if you're doing it from the beginning, really what you want to do is define your objective. And sometimes you don't know when you start, and you have to go back to it. So a lot of times it is, minimize something. And in reality, it can be a lot of factors. We mentioned about, a few already here, the material and the manufacturing. So if I'm going to pick an alloy, for example, that I can't weld for a certain application, aircrafts don't use a lot of welding, you use some. But if I'm in a general application and I'm picking an alloy, it's really good quality, but I can't weld it, it's likely that it's going to be more expensive to put it together. So it's one of those considerations where if I'm trying to minimize the cost, for example, in the context of the aircraft, it means a big consideration on weight and a big consideration on manufacturing. And then material, yeah, it is part of the equation, but it's not necessarily, it's definitely not the end of the road to just pick a book and say, okay, this alloy is 20% cheaper and it's the same strength. Good. There's just a whole lot more to it. So this is a schematic. Again, it may or may not be current, but it's got different colors. If you look at the pink on top, that's an aluminum alloy of 7000 series that goes on the top of the fuselage. And when you look at the blue on the side and also a little bit on the wings, it's a 2000 series aluminum. These two alloys are fairly different in terms of their strength. The 7000's got a bigger yield strength, the 7000 series, but it's got a lower crack resistance. So depending on what you're doing, if we're looking at it here, this is on top. There's going to be some tension. There's going to be a whole bunch of factors that you have to decide what exactly is the governing criteria. Now, the governing criteria over here is we're going to talk about constraints. We don't build any aircraft with the idea that we're going to optimize its strength. We're only going to make it strong enough for the application. So over here, you can have, strength. There's an aspect of reliability which is different. And then there's durability. These are general terms here, but you can include in here corrosion resistance, crack propagation resistance, the risk of having a brittle behavior. These are all aspects that you have to deal with. But that's not really the goal. The goal is to find what's going to fulfill all the requirements. So think of the constraint as the requirement, and at the same time, help you overall with something. A lot of times it is cost. But again, cost here takes a lot of dimension, it takes the dimension of density. What I will do today is show you some kind of high-level ways to think about material selection. But I do want to tell you, even in a sophisticated industry like aerospace and aircrafts, sometimes it is based on experience, and it is not an obvious decision between, for example, using steel, using a titanium alloy, or using an aluminum alloy. I remember having meetings where we had to change some components holding the landing gear for the aircraft because in the testing, so when you test the aircrafts, you have all sorts of levels. You do very small assembly, you do material testing, you do sub-assembly testing, and then you do the full assembly testing. So they had all of these done, and when they got to the full assembly testing, they were getting cracks on a big transfer box that was taking the load from the landing gears, essentially connect from the landing gear to the mainframe. And it wasn't really a material issue, it's just in design they had forgotten to measure stresses, to calculate the stresses in a certain direction. So it was a little bit more of a design issue, but what it came down to is they only had so much space then. And they wanted to find a fix that will meet all the other constraints. And then the material selection started going again. Are we going to switch to steel for this component instead of aluminum? And the idea of titanium also came along just so. And what was interesting is we didn't have necessarily all the documentation to say, okay, this is how we decided originally to use aluminum. This is all the studies we did. You know, it's great. Now we have this change, which is it needs to be stronger in this particular direction. What are we going to do? And just change that study. It was unfortunately more from experience. They had used aluminum in previous generations. A lot of times they will sell the aircraft for a certain weight, and then when it comes to the very final design, it's just like building a car in different weight categories. There's a certain limit you can't exceed. So if you have a little allowance and this is your last change, you can go to steel and just don't have to change any of the design, for example. That's a big advantage. Or you may be a little bit overweight, and then now you have to switch to titanium. And it's a little unfortunate, but I've seen it several times where it's close to the end of the whole process, the whole assembly, and you think you have it all together. You look at it here, you've got some green stuff in the back. These are where the composites are used. So you wouldn't want to go very drastic and say, let's go back to an aluminum tail. That wouldn't fly. But some of those components that sometimes can go one way or the other, depending on the detail, is really where the attention comes. So one of them that I actually worked on is the leading edge of the wings. When it's in closed position, there's not a whole lot of load into it, but what happens with the leading edge on a lot of aircrafts, it's extending and it's bending forward to create a turbulence and essentially float the aircraft at lower speed when you take off and land. So some of the motors you hear when you take to the aircraft are related to just getting these components in and out, essentially. When it's in an outward position, what you have is you only holding it on kind of a piston system. So I'll show you here an example of what it looks like. So you have 2 attachment points only. And this component here is the titanium alloy, and it's the same that is in green here. The only difference is this was primed because it was going to be in contact with all the aluminum fuselage. Just to give you an idea of size, you're looking at about 4 inches for the 2 sides of this rib. The width of the rib, and then in the web portion, it's only about 1/8 of an inch or 3 millimeters. It's very small. So all across here, we're looking at about 2-3 feet. So what happens with the leading edge on most aircrafts is you have a de-icing system. That's something that is circulating. That's the reason also for the big hole. So the air is circulating. If you have an ice condition, you recirculate air from the engine to keep this warm. Through years of trial and error, putting thermocouples in the wings, they have essentially a history of the range of temperatures you could expect here. And for this particular model, they could not convince themselves that they would always be, say, below about, they couldn't promise below 200 degrees centigrade. So what it meant in terms of material selection, this is one of those charts. It's a very simple one. That's where we're starting here. It has strength as a function of the maximum service temperature. So aluminum is very widely used for aircrafts, and you can see here, if you look at that bubble, they're all red, unfortunately. So aluminum alloy is this one, and the horizontal axis is a logarithmic scale. So here we are at 200 degrees centigrade. So even with the best, the more resistant aluminum alloy for temperature, you would be above the limit here if you go to 200 degrees centigrade. Now, they had ways where you would have the alloy essentially heat treated. You can use different series. So you could say, okay, well, because I have this heat condition, I'm going to use an aluminum alloy that requires a heat treatment at a higher temperature to get soft. And that brings me back to something I mentioned in the introduction lecture, which is the way we make all aluminum stronger, anything that's on the aircraft, is quench and age. When you quench it, you essentially take the entire microstructure and you keep it as is. It's very soft at that point. And when you go through the aging treatment is where you form these little precipitates. So if you have an alloy where those precipitates are more stable with temperature, when you heat them up, you have to go to greater temperature to have your softening zone. That's where you may be able to get your 200 degrees centigrade. But typically the alloys that we're looking at for the aircrafts are not the more temperature resistant. They're very optimized for strength and toughness. So it'd be even less than 200 degree that you can use that. So in terms of the exercise of material selection here, what's going to be happening to the frame here, this rib? In terms of loading, it's really going to be loaded only when you put it out and you take it back. So every flight's going to have this big cycle of no use to maximum use, and there may be a few big cycles of fluctuation from the wind that you have to take into account. But in terms of the essentially number of cycles before you have to retire, it's not super high. That's what we call low cycle fatigue. And I don't want to get too out of range here, but if you think of vibration, it happens very quickly. It happens a lot of times, 5 hertz, many times per second. So you're going to have a lot of cycles through the life of a component. If you talk about the wheels for a train, for example, that is very high cycle fatigue. When we're looking here at 30,000 cycles, for example, in terms of fatigue for a structural component, it's fairly low. You know, it happens a couple times per day, essentially, through the life of the aircrafts. And we do differentiate that. I'll put it here because I'm going to come back to this. So we say low cycle fatigue is what we find the more prevalent situation here. There are different views on this, but I think there is somewhat of a consensus that is up to 200,000 cycles. A lot of times in low cycle fatigue, you're going to reach the yield strength of the material. You're going to have some permanent deformation happening, and that's why it will fail very quickly. And when we call about high cycle fatigue, it may be a little counterintuitive, but it doesn't mean high load. It essentially means high number of cycles. So that is what's beyond that. And typically we're going to keep track of values like 10 to the 6 cycle, 10 to the 7 cycle, are typical values that we're looking at. These are big numbers of cycles. You can go higher if it's really vibration. So over here, this is not what we have. We're not interested in this type of behavior for this specific situation. We're very interested in what's happening when you have very few cycles. Now, there is another thing to keep in mind, and this is a fairly high demand application, but you need a lot of reliability. If you have a collision, big birds, you test the engines with these chickens and stuff, and you need to have the impact resistance at the same time as you have this reliability. So in terms of what we're looking in terms of resistance, we do need a minimum strength. So I'll put the strength here for, I call it incidental loads. And part of the strength here, I think really, I would think we want to have some toughness. And that is really related to this idea that if I come and somehow there's a problem with the material, there's a crack in it, and I didn't find it in inspection, I didn't find it when I did the original manufacturing, I still would like to not completely fail. You know, if it deforms, that's one thing, goes out of shape, but the idea that all of a sudden this component will just break in two pieces, not exciting. Another aspect that's particular to this situation here is the way we look at it now. This one you can inspect it on one side, but you can't really inspect it on the other side, even with non-destructive technique. So this idea that you would, you know, allow for a certain crack to grow, see it, find it, and then fix it is not really appropriate here. You essentially have to take the whole wing apart if you wanted to do that. Other structures, just so you know, on the fuselage itself, lots of times you expect cracks in some location. You don't know where they're going to be. But because of, you know, salts, for example, in certain environments, the fuselage can crack, but it's designed so you will see it. You will be able to identify it through non-destructive testing and repair. So again, this is not an option for this particular case. Now, the environment in this specific condition is really more of a simple constraint. You know, the material is going to keep its strength or it's not. If over time, if it gets to the maximum heating temperature and I lose half my strength, then I'm almost certain that my design's not going to work anymore. So this actually really helped in this particular case. It essentially said, because this is primary structure, we don't want to take a chance, and we're not going to use aluminum. And that's how it was done for years and years and years. They were using wrought titanium, essentially 4-inch thick plate. So if we go the way they were doing this, so you start ready to scale, so 4-inch about this. You buy this plate, and out of 4 inches or say 100 millimeters, you are machining down to about 3 millimeters. The reason they were doing this is instead of a casting, for example, is you can predict better, you can have a very much more homogeneous microstructure and material characteristics when it's being wrought, when it's being cast, deformed, and everything. So the initial idea was, we're not going to take a risk. All we want is all of this to work out, know all these values, and go and fly. Now, of course, 10 years down the road, one project I was involved with was, okay, this has been working. Now, could we do a casting of it? Because we would save a lot of money in terms of machining cost, in terms of the cost of raw material as well. Now, this is a little bit specific to titanium. So titanium alloys, you can cast them a lot of times and get very good properties. When we're talking about the fracture toughness, you can have almost as good of a fracture toughness as cast that you get out of the rock product. Fatigue resistance, you know, somewhat similar. The only problem really was this risk of having an imperfection from casting, a big porosity on the surface, and inclusion from the mold, something that you just didn't expect. So the only practical way it was going to be allowed, essentially, and so there is some aspect of regulations in doing this, was to have a lot of non-destructive inspection done before these are but it was essentially at that point more of a question of substitution. So they had something that was existing, and the goal was to say, all right, what's existing has this, and this property. We can meet all of those. And then the one thing that is a little bit more difficult is, are we going to meet them all the time? Because now we change our way of manufacturing. So this became a little bit more beyond just a simple material selection, of course, but if we're going back here to trying to resolve how we're going to do this between strength, toughness, and fatigue, a lot of times to meet the regulation requirement, you do have to make sure your strength is good. So that always, it's very surprising. I always got surprised, for example, that before you can use a piece of titanium on an aircraft, you have to do 100 tensile tests from different vendors, from different batches. So it's listed in the military handbook, and this is, you know, the minimum that you're going to get out of everybody making it to this standard. What was interesting to me is when you get into the topic of toughness, and then I'll say crack resistance. This was a little bit more of a gray area from my understanding anyway, that yes, you do design for damage tolerance, but there are a lot of parameters, and these are not properties that are very easy to measure. So it becomes an overall program evaluation as opposed to a very prescriptive list of things that you have to meet. And there is a reason for it. So let's go through this how fatigue happens and how we characterize it. So I have a material, I'm just showing essentially a stress riser. Most of the time when you have crack initiating by fatigue into the material, there is something in there. You know, it could be a rivet, it could be just a corner. If we're talking about the rivet, it's going to be this place where there's more stressors. So if in that little corner that has more stresses, you have this local plasticity, and that's when I was talking here about the low cycle fatigue. If you have a little bit of plasticity, you know you're going to fail quickly, and the way to characterize that failure a lot of times is to do a specimen that doesn't have a crack in it, and then you initiate and grow that crack over time. So in red here is the specimen that didn't have a crack, and what you do is you find out for a certain load how much time it takes before it breaks. So these are called stress and number of cycle curve. And they're very, very common. They were not applicable to this situation. This situation, because of reliability, we had to assume that there was already a crack in this rib. So the experiment in the laboratory, the data used to determine whether you're going to have a failure or not is a pre-cracked specimen. This is a compact tension specimen. You make a notch and then you start a crack, and then you can do a number of things. You can just pull it until it breaks. That's really a fracture toughness test. Or you can continue to cycle it, grow the crack. So you have a crack growth rate here as a function of how much load you apply to it, the stress intensity. So essentially, that when we don't say stress here, we say stress intensity because it's taking into account the crack length. That's really the difference. This is the approach that is appropriate for a lot of the aircraft fuselage because we talked about the wing, but the whole fuselage goes through this pressurization cycle from being on the ground to all the way in the air, where you have a lot more internal pressure in the aircraft than you have external pressure. So these are the main loading cycles. And you can keep track of them. You assume that you already have a crack to begin with, and you want to know if that crack is going to grow to a critical length. So critical length for this specific plate essentially means, and I'm going to blow up here this analysis. Delta K here is our variation in stress intensity, and just for our purpose, K is just going to be a proportion of the stress level and the crack length. K is the crack length here. So it essentially just combines the two. It combines what is the nominal load applied, and it also includes how the crack length is. So if I have a bigger crack with a smaller stress, it's the same K that a big stress and almost no crack. That's kind of how to think of it. It's a compounded factor. So we were essentially saying here, how are we going to predict the life? How are we going to make sure it's safe? So over here we have the growth of the crack over time. Eventually, it will fail. So I'm going to just say here that the K is reaching the K critical, just for our purpose. And that K critical here is the fracture toughness of the material. Let's see if we can do this together. We don't want to go there. We don't want the combination of the stress and the crack length to be sufficient that all of a sudden. So this is where, it's very important for you to keep in mind. This is essentially the capacity, and this is the demand. So when I'm writing this here, this is just the demand. And I don't want to get into the situation where I reach the material characteristic, the KC. So what it means is, at most, at the end of the life, I'll put a factor on it. I'll say, I only want to be, say, about 1/3. So I'll say here, K is KC over 3. And then, so that defines where I want to be at, we said, I think 30,000 cycles. In our example, this is, of course, a little bit of fiction here. From the manufacturing, from all the quality control testing is done. You can do liquid penetrant. We can go through some details later in the class on all the qualification testing you can do here. But say you manage to know from the service condition that you cannot have an initial K, so we could call Ki here for initial, that is at most this value. So what's left to do essentially is arrive to an equation that's dependent on the material and how you're going to go from your initial condition to your final condition. And it happens to be that we're plotting it in a convenient way because most material for aircraft application will have this linearity between the crack growth rate and the stress intensity when you put it on a log scale. This is the logarithmic scale. So I'm really throwing a lot at you. Yes?
What's the n in the y-axis? Do you have the n?
How much the crack length is changing by number of cycles.
Oh, number of cycles.
Yeah, good question. So if I go back to my material selection here, now that I've identified how it's going to fail, this is kind of our failure model for this complex situation. We know this value, the KC, is going to be an important factor because it's determined where this line lays. And then the other factor is how much the crack is going to grow over time here. And that varies from one material to the other. I have some curves here just to show that nothing is perfect in this world. This is one alloy. It's pure titanium. And you can see the spread in the data. So when you see this level of spread of the data, you can probably understand better when I said this needs to be done. We'll believe you when you test it. Is a little bit the approach that they're using. That's why we have to do a lot of full-scale wing tests on aircrafts, because you can't guarantee that all this data actually means what it means for the application. But it's a really good process to at least know, they built aircrafts before they were able to use this approach, by the way, okay? So this is not the only way to do it. But if you can rationalize it this way, especially if we're talking about material substitution, you're starting to know what you're going to be looking for in terms of equivalency.
They built them, but they also crashed them more often too.
Yes, they did. There was some, you could go through a lot of case studies on the aircrafts. One of the first mistakes they did is they were making square windows. So they had a lot. Yes, you're going to talk about this?
He has a question.
Oh, I'm sorry.
I was just wondering, so is it strategic to, I would assume, to be at different places on that curve where you wouldn't want your crack growth to be occurring at a fast rate? So
yeah, it happens that way. So it's not linear at the very beginning, and it's not linear at the end.
So I would imagine being at that very beginning, if your critical point happened to come right after a large slope, that would be a situation you don't want, because you wouldn't have as much time to see it potentially? Or is it really driven by the delta K, or where you also fall on the curve? Is that taken into account?
The question was, I made this our life easier here because we were in the linear portion. I said the K was already in the linear portion. It's not the case for all applications. There will be applications, if you're looking at a pressure vessel, for example, where the demand is low, and you're going to want to take advantage of that in your prediction. The problem here is because it's aviation, you have to assume that the initial defect is at least this big, and because we're dealing with aluminum, a lot of times we are starting to be linear. And if we were not, for the purpose of a calculation, we probably would assume that it is. And one of the reasons for that goes a little bit beyond what I wanted to do here, but these curves, when you do the initial part, it's difficult because it's essentially studying the crack at a very, very small speed. And a lot of times what we do with those specimens, if we go back here, I mentioned we make that crack. We make this relatively fast typically. And then what we try to do a lot of times is we slow down the experiment to try to get these very low rates. But from one way to slow down to another way, this initial portion of the curve is not always the same. So it's as you go through the, you're right that the more critical component is when it's going very, very slow. It's the portion where this whole concept of fracture toughness and stress intensity is least useful, unfortunately. Yes, very good.
Just say something up here. This area that you were just talking about is the area of what they call small crack growth.
No, we don't want to do small crack growth.
No, I know. But the point is, this thing actually can go like this, it can go like this, it can go like this.
Yep.
It can go in all directions down here, depending on the inclusions, the residual stresses, okay, and the inclusions create residual stresses, other small minor imperfections. So there's lots of noise down here, which is why Dr. Belmar's kind of wanted to say, let's not get into that, okay? For your information, the guy who did his doctoral thesis on this about 25 years ago was Jim Carosella.
One of them, right?
One of them, yeah. But anyway.
It was a very popular topic in the 70s and 80s. to understand better the effect of the material, the effect of being increasing the load, decreasing the load. So I think the one thing we didn't go back to in our discussion was the square window. So if you had a square window instead of a rounded corner, you have a lot more risk to initiate a crack. You could reach a condition of plasticity very early on, so you have a guaranteed in crack initiation, and that crack is one of those short cracks. So what Professor Eager was mentioning is you don't know what's going on necessarily here, and actually when you have a very sharp corner, you can create a certain blunting when you do tension and compression that's going to make this initiation of the crack a lot faster. It's essentially just the idea that you're stretching from a square, and it's not something we can characterize with K, but you can have a lot of speed on initiating the crack. You can get the crack much bigger very quickly, and then the growth of it can be very fast. All right, so this really was the more sophisticated way to think about the crack propagation. Now let's go back to how we normally approach a design problem or challenge. So let's forget about this complex stuff for now. We'll go back a little bit to the damage tolerant. This was damage tolerant approach to design. Later, when we talk about factor of safety. So I have a general application. Maybe all I want to do, you know what, is make sure that my beam is not going to deflect by a certain amount, for example. The wing, it's actually not relevant to the wing, but maybe we take it this way. We take the turbine blades of the engine. We don't want them to lengthen more than a certain amount when they go from unstressed to the stress condition, because they have to fit very, very tightly into the shroud. So that'd be a situation where we want something that's a high modulus and low density. So what you see in this representation is a lot of dots. So density here, Young's modulus, and then you have all these curves. And we'll go to the meaning of them, because the difference in these curves is how you rate the importance of stiffness as opposed to density. So you can have a situation, if it's just a tension application, all you really care is the ratio of the stiffness over the density. But there's going to be other application in bending where you're going to be interested in another ratio. So here, if it's in tension, what you see is you'd like to have a bunch of ceramics. You may be interested in glass. I mean, I doubt it if it's really a structural application. But this is the sort of high-level information that you can get. If you're in a bending application, I'll tell you right now, you can be interested in this type of slope. So over here, if you want something really stiff, is where you may be interested in just a polymer foam, for example, that for the weight, it will provide you in bending the best stiffness. That is providing that you have space for it. So there are a lot of ways to design for bending. And that's where we're going to go next. So if I'm interested in maximizing the strength, for example, for a certain density of the material, I have this table here. This was from the just the metals handbook. A lot of times you are loaded in either tension or bending. In tension, it's just the failure strength or the maximum usage strength divided by the density. If you're into a beam, is where these ratio changes. Now, I'll go over why, because if you remember our objective for now anyway, say we want to minimize density. So that's the weight. So we'll put weight really is density. And say we have a beam that has a width and a height and a length. All right. What else do I know here? This is what I'm trying to do. And I know in bending that stress becomes important. So my stress is going to be proportional to the width of the beam, the height of the beam to the square. The length doesn't necessarily matter when pure bending. So let's just do it this way. So what I do then is I take the height, because I don't want to solve for the height here. What I want to say is I'll make my beam whatever high it needs to be to fit my application. So that tells me that the height is proportional to the square root of my stress and I guess other factors. You don't really want to know everything else. So all you need to do at that point is substitute this here. It's 1 over. Okay, yeah. So if you substitute it here, you'll see that the density has an importance, and then the strength of the material is only going to have an importance of 1/2 into my objective, and that is where we have here for a plate. If you have a plate, say at the floor of the aircraft, a lot of times you use honeycomb structures, so it's not exactly worked that way, but the floor is loaded and bending. All you want to do is optimize the density first. That's really the most important factor, and strength is another factor. In this example, we don't care about the amount of deflection, for example, that we get out of the floor. As long as it's far from the failure point, it's good. So, as opposed, if you're in tension, a lot of times steel is great because you compare it, strength over density is your performance index. If you're loaded in bending, you're more likely to select a lower density material. So we talked about foam, we're talking here about aluminum because the strength is not become less important than the density in the region. So if you see those charts, I'm going to have to break it here and we'll take it over next time. If you take these charts and you see this ratio, there's one for strength. Okay. That's exactly what we're looking at. So this specific line here is for a plate loaded and bending. And this is a member loaded in tension. So if I have a plate loaded and bending, I want to minimize the weight for sufficient strength. Is where if I could, if the space allowed, I would use porous material, rigid polymers. We're not talking about elastomers here, we're talking about PVC, for example. So silver PVC would be a good material. Wood would be pretty good. And then you get into the composites over there. This one here is pretty high up. The metals is where we were going to load them in tension. So if we have this slope and I draw a line right here, I'm going to hit the metals before I hit any wood or anything else because now I'm loading in tension. So it's a very good screening, and I think it can help you understand that the basic application of how you're loading. You have these charts not only for mechanical properties, you have them also for conductivity, all the thermal properties. You can have them for shock resistance. there's about, hundreds of these, and you can make your own too. But it essentially is all based, just to finish it up here, on what am I trying to do and what really are the constraints. And in some cases, you have a lot. Sometimes it's not very quantitative. For temperature, if you remember, it was a pass or fail. You're going to change or you're not going to change, and then I'm done with you. For another, just a general application, when you're at the beginnings, trying to say, okay, well, I have this. Think about, just to finish it up here, I have a big tube for a bicycle. And somehow I decided my tube is going to be this big from a design standpoint. Now, for the different material, what I can do is just vary the thickness of that tube. And if I'm not worried about denting it, what it will mean, if I'm just varying the thickness here, is the strength and the density are the same importance. That's going back to our strength equation, so we're going to have the stress proportional to the stiffness of this here, because the stress level is just going to change linearly. We have a fixed size here. This is a big tube, so the moment the section modulus doesn't change. So if we're able to do that, most likely we'll use steel. The problem is now there's other constraint, the resistance to buckling that's going to come into play, that's going to change the solution, but not from a simple bending equation at that point. It's going to be other consideration that we have to put in. Thank you, guys. And we'll continue on next week. Our next weekend is continuing.
Did you read your email?